All right, so how do decimals and rational numbers get along? So I mentioned earlier, and hopefully you remember this from the previous chapter, rational has the root ratio, and these are what we call fractions. And we use the word decimals a little bit different than its technical meaning, right? Technically, decimal is anything based on 10, so our whole numbers are decimals. So what we really mean here are decimal fractions. We already looked at how to convert fractions into decimals, right? All we have to do is read it properly. So for example, 25 hundredths is literally 25 hundredths, and then I can reduce if necessary. Here I can see 25 goes into 100, so 25 is the greatest common divisor, and so that's the same as 1/4. So decimals to fractions, pretty easy, read properly. When I'm trying to go the other way, I want to take a fraction and turn it into a decimal. Well, a fraction, in addition to be a ratio, is a division. So that means I have to actually act on this division, 1 divided by 4, which I can do on a calculator or without, and so we're going to look at it both ways. So I could also translate that using the long division, or the goes into symbol. 4 goes into 1 how many times? Now we know this isn't a whole number, so at first we get 4 goes into 1 0 times. But we've learned the trick that 1 is the same thing as 1 and no tenths, which is the same thing as 1 and no hundredths, or 1 and no thousandths. Okay, we can put 0, tenths, hundredths, thousandths, or any other place value we want in the decimal fraction section. So what we do is we say, okay, what if it was going into 1 and no tenths? We can continue here. The trick, we'll learn more about this later, of dividing with decimals is to know where the decimal goes in the dividend, because then that tells you where the decimal goes in the quotient. Okay. So one key thing we need to know, the decimal in dividend determines the decimal in the quotient. There we go. Once we've established that fact there, then we can just ignore that decimal point and move on. So now this is like saying, okay, 4 goes into 10. How many times does 4 go into 10? Well, 4 goes into 10 twice, because 2 times 4 is 8. If I tried 3, I would get a 12, and it wouldn't work. I subtract, I have a remainder. Now, a remainder is a fraction, 2 out of 4. I don't want to mix fractions with decimals, even though I could, right? So hopefully you remember learning that we put another 0 here to continue. And I can bring down that 0. 4 goes into 20, how many times? Well, 4 goes into 25 times. 5 times 4 is 20, and I get a 0 remainder, right? So that indicates that I'm done and I did the conversion. So decimals to fractions, all you have to do is read it properly. Fractions to decimals, you have to actually divide. And sometimes that's easy and sometimes it's not. Do all those divisions always come out nice? The answer is no. Let's play with a calculator for a minute. Calculator today. So on a calculator, for example, if I type 1 divided by 3, that's the fraction 1/3. The calculator just interprets it as a division. 3 goes into 1, and it's programmed to use decimals, and it gives me a whole bunch of 3s here. Now, let's see, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 threes. I'm just going to whip out another calculator just for fun. I'm not sure if you guys have heard of the Desmos calculator. This is the scientific version. 1 divided by 3. And Desmos gave me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Huh. Which is it? Is it 0.333333333 10 threes, or is it 0.3333333 11 threes? Which calculator's right? Those are two different numbers. Uh-oh. Do my calculators really disagree? 1/3, according to Google, is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. According to Desmos' calculator, it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That place is missing. What's going on here? Those aren't the same number. They're close, but they're not the same. Any thoughts? It's repeated forever. How do you know that's repeated forever? Forever. Eek. I can't live forever. So it's, come on, pen, right, please. There we go. So it's really 0.33333 forever and ever, never stop making threes. It's getting painful. Uh-oh, I'm running out of room. What does it mean to go on forever? Like even with this many threes, I don't even know what to call this. Do I know these? Let's see. Tenths, hundredths, thousandths, 10,000, 100,000s, millions, 10 millionths, what's next? 100 millionths, billions, 10 billions, 100 billions. Okay. Okay, so I can name it. That's hard to read. All right, so we got a little problem here, right? So one is the calculators don't always agree. Some calculators show more decimal places than others. If you have a handheld calculator or a phone calculator, you might whip that out and see how many threes it gives you. And then the other idea is what does this forever mean? So let's explore the forever idea. That sounds exciting. Forever. So again, to get this, a division happened. So we're looking at that as 1 divided by 3. In other words, we're going to take 3 into 1. Now, we know that 3 doesn't go into 1 a whole number of times. So 3 goes into 1 0 times. The trick then is to say, okay, we'll just put a point there so we know the decimal point goes there. And then we can put as many zeros here as we want. So maybe I'll put 4 of them there for now. So then once I know where the decimal place goes in the answer, that's the key to doing division with decimals. And again, we'll get to that in the next section. My hope is you just remember that from your past life. Now I can read this as 3 goes into 10. Okay, 3 goes into 10 3 times. 3 times 3 is 9, and I get a remainder of 1 and bring down to 0. 3 goes into 10. Oh, wait, this looks familiar. 3 times 3 is 9. Subtract, get a remainder of 1. Bring down to 0. 3 goes into 10. Okay, I think I see the forever part now. See what I'm getting at? The same thing happens over and over again. I'm always going to get a remainder. 3 times 3 is 9. Subtract, I get a 1. Bring down the next 0. And I can keep putting zeros here. Now, I literally can't go on forever. So that isn't an ethical, is it ethical? No, it's a philosophical debate. But I don't want to go there right now. But I do have this problem is that I always get a remainder of 1, and it's always 3 times 3 is 9, which is as close as I can get to 10 without going over, and I still get that remainder of 1. And interesting. What's repeating here? Well, there's actually 2 things repeating here. Switch color. This 3 seems to be a repeat. And this 1 is also a repeat. Okay, so I got a couple things going on there as far as the repeat goes. So we're going to try another example. Let's whip out the calculator and then test it. So how about, let's do 11ths. 11th's a nice number. No, yeah, 11's nice. I like 11. So what if I took 3 and divided by 11? So 3 11ths as a decimal, 0.27272727.2. If I ask Desmos, what is 3 11ths? It says it's 2727272727. So this one ends in a 7. Does it really end? So here's one question. How do I know that it didn't just stop there on its own? Like, how do you know when it stops and when it doesn't? When does this forever come in? When does the decimal repeat forever? When does it stop? How can we figure that out? Does this one really stop, or does it repeat forever? Desmos stopped at a 7. Google went one more place and said, hey, there's a 2 after that 7. Is there really a 7 next? How do we know that? All right, so now we're going to check that out. Let's try that by using division. So Desmos and GeoGebra were both doing something like long division in the background. They just didn't show it. They just spit out the answer. So we have 3/7, the fraction, which is really 3 divided by 7. Or I can say, let's let 7 go into 3. Now, 7 doesn't go into 3 a whole number of times, so we do that trick where we say, okay, just put a decimal there and throw some zeros. Oh, no, not 7. I want 11. I lied. 7th is a whole nother animal I'm not quite ready for. There we go. So we'll throw some zeros there. And the question is, we never know how many zeros we need ahead of time, unless we're good at looking at the calculator to figure that out. 11 goes into 3 0 times. I think that's important to note because I know where the decimal goes right there. After that, I can kind of ignore the decimal. 11 goes into 30, 2 times, but not 3, because 2 times 11 is 22, and 30 minus 22 is 8, and 8 is smaller than 11. So 2 is as many as I can take, and then I bring down the 0. Let's see, 11 goes into 80. How many times do you think? 7. Thank you so much for playing. You rock, Monty. 7 times 11 is 77, and 80 minus 77 is 3. Bring down the next 0. Okay, so 11 goes into 30. How many times? Wait, we've done that before. It's up here. It goes in twice. So I've actually seen the 3 and the 0 before in the beginning. There's that same 30 I'm trying to go into again. So I think that before I even wrote that 2 down, I see a repeat right here. And we're just going to keep going a little further to double check this. So 2 times 11 is 22. We subtract, we get the 8, we bring down the 0. Wait, we've seen that 8 and 80 before, and so now we see the repeating cycle. And it turns out the remainder is more important than the numerator, and we'll see that in a minute. So the repeat started here. So I'm going to draw a red line. So this section is going to repeat over and over again because we're going to see a remainder of 8 and then a remainder of 3 and then a remainder of 8 and then a remainder of 3. And those are how I decided to put the 7 or the 2 up here. So it's my claim that the repeating remainder is more important. And that happened right there. All right, let's look at another one. Let's take, for example, oops, wrong way. 1/6, which is really 1 divided by 6. Is that going to be nice or naughty? Naughty meaning it keeps going forever. It's kind of naughty. So if we're not sure, we could always check on a calculator. Okay, so will this 1 ever turn up again? Could it be right after that 6? Huh, I don't know. Could be. It's possible. Let's find out. The only way to really know for sure is to actually carry out the division and look at the remainders. So this means 6 goes into 1 how many times? Well, we know 6 goes into 1 0 times, so we have to put our decimal in and see what happens. So let's see, 6 goes into 1 no times, 6 goes into 10 once. 1 times 6 is 6. Subtract, we get a 4, bring down the 0. 6 goes into 40. 6 times 6 is 36. 6 times 7 is 42. Yeah, let's put a 6 there. 6 times 6 is 36. And I get a remainder of 6. And I'm saying, whoa, check it out. We get a repeat. So the repeat happened. This time the repeat was the, oh wait, I did something wrong. Shit, undo. What's 40 divided by 40 minus 36? Thank you. Nancy's all over this, she's got me. 4, okay. So that's the repeat I wanted. Yeah, I was looking back up and was saying 6 is not a remainder. So the repeated 4 happens here, but it's not related to the top. So notice there's a little delay before the repeat, and that can happen. Sometimes the delay can go on for a while before the repeat kicks in. It just depends on the numbers we're dealing with. So once I see the repeated remainder, I know what happens up here. So here I have 1 repeated part of the remainder, just the 4 repeats, and so only the 6 is going to repeat here. Whereas in this one over here, I had a repeating 3, and I'm going to have a repeating 8. And because there's 2 repeating remainders, I get 2 digits that end up in the quotient that are going to repeat. And so the repeat depends on the repeating remainder. And remainders are kind of interesting. When I'm dividing by 11, what's the biggest remainder I can have? Anyone? What's the biggest remainder I can have in dividing by 11? Not 9. Good guess, though. $10, yeah. It turns out the biggest remainder is always 1 smaller than the number. So 10 is the biggest remainder I can have when dividing by 11. What about dividing by 6? What's the biggest remainder I can have when dividing by 6? 5. So when we're thinking about the possible remainders we can have, now we could have a remainder of 0, but that means the division ended. If you have a 0 remainder, you're done, no repeats. So we're thinking about things that repeat. So as far as repeating remainders, if I'm dividing by 6, the remainder could either be 1, 2, 3, 4, or 5. So I have 5 possibilities. So, and think about 11. For 11, If we have a 0 remainder, that means we stop. There's no termination. It doesn't keep going forever, so who cares? But if it doesn't terminate, right, I didn't get a 0 remainder, that means I have 10 possible remainders I could get. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 when I'm dividing by 11. And that's related to the numerator. So the way to think about this is when you're dividing by a number, like dividing by 11, at most I can have 10 steps in my division before I have to repeat a remainder. When I'm dividing by 6, I can have at most 5 steps in my division before I have to repeat a remainder, because I run out of remainders, right? There's only 5 of them. So let's do another example. We're ready for 7 now. Let's look at, how about 3/7, which is 3 divided by 7, or 7 goes into 3. So this time I'm going to try and do it and then look at the calculator to compare. So 7 goes into 3 0 times, and so I need to put the decimal point here, and then I can put as many zeros as I want there, and then start dividing. So let's see, 7 goes into 30, what, 4 times? 4 times 7 is 28. Subtract, and I get a 2 remainder, bring down the 0. 7 goes into 20 twice. 2 times 7 is 14. Please, somebody make a note if I screw anything up here. 20 minus 14 on a good day is 6. Bring down the 0. 7 goes into 60. 8 times? 8 times 7 is 56. I think as close as we can get. Subtract, and I get a, what, a 4. Right, so far, just what have I seen for remainders? I've had a 2 as a remainder. I've got a 6 as a remainder. Now I have a 4 as a remainder, right? So no repeat next. 7 for remainders can have 0, 1, 2, 3, 4, 5, or 6. Those are the only possible remainders. Okay, if it's 0, we're done. I'm assuming we're not going to be done here. Bring down the 0. So 1, 2, 3, I have 4 zeros, and if it doesn't end here, I need more, right? What, 5 times? 5 times 7 is 35. I need another 0. Bring it down. Ooh, so close. 7 times 7 is 49. Didn't quite make it. Remainder 1. Have I repeated any remainders yet? So what have my remainders been? 3, 6, 4, 5, now 1. What number's missing? 1, 2, 4, 5, 6. 3 is missing. Wait, there's a 3 right there. Does that count? Interesting. Let's keep going. So I'm here. I need another 0. Bring it down. 7 goes in there once. 1 times 7 is 7. Subtract, and I get a 3. Do I need another 0? 7 goes into 30. That sounds familiar. Oh, we did that right here at the top. Okay. So it turns out that initial 3 up here is kind of part of my remainder because it is a fraction, right? It's part of this whole 7. And so I actually do repeat that 3 remainder right here. So I'm going to draw a little line right there. That's where the repeat starts because I'm seeing another 3. And I had a 3 right there. And so that takes me to this point right there. And so again, what would have been next here? 4 times 7 is 28, right? And I have that 28 up there repeating, and then the same stuff's going to keep happening. So it's going to be 4, 2, 8, 5, 7, 1. 4, 2, 8, 5, 7, 1. And the misleading thing for kids that aren't familiar with using calculators and decimals is that a lot of calculators are going to round in certain places. Like if a calculator wanted to stop there, it would call that a 4-3. Right? So let's whip out a couple calculators, see what happens. So this is 3/7. And Google says 428,571, 42857. Next would have been a 1, so rounding isn't too much of a problem. The 7 didn't get rounded up to an 8. What about Desmos? 3 divided by 7. Notice Desmos says 8/6 here, because it's rounding what would be a 5 next, and then the 7 up, right? So different calculators give slightly different results depending on how many decimal places it shows